Okay, everyone, welcome back to part 2 of section 17.2, taking first order partial derivatives still. So we're going to start up here with this example. Okay, what are we looking at here? I have 8 times e raised to the quantity 7x minus y. I know what I need to do. I need to use the derivative rules for e to the x. Now I remember the derivative e to the x, which is plain old e to the x, and the derivative of e to the u was e to the u times u prime. So these are the rules we're going to be working with here. Our derivative rules is just when we take this derivative there, that will be not a plain old derivative, it'll be a partial derivative with respect to the appropriate variable. All right, so I'm going to get rid of this here. Put the important part up here as a little note to myself. And go ahead and get started. All right, so let's see. The first order partial with respect to x is going to be e to the u. Okay, so the 8's a constant, or coefficient, so it drags along. E to the 7x is going to be e to the 7x minus y times, and now I need to take the derivative of the exponent, but not the derivative, the partial derivative with respect to x. Well, the partial with respect to x of 7x will be 7, and the partial with negative y will just be 0 because there's no x in it. It's just a constant. And then I'll clean that up. And properly label it. And there we go, our partial with respect to x. That wasn't too bad. Well, let's go ahead and then do the partial with respect to y. Okay, red, yeah. The first order partial with respect to y. Let's see, 8's a coefficient, e to the u times the partial of u with respect to y. Well, that'll just be a negative 1 then. And so I get negative 8 e to the 7x minus y. Nothing more I can do with that, so let's go ahead and properly name it. The first order partial of f with respect to y is negative 8 e to the 7x minus y. All right, how about this one? That's a mess, but I remember the rules. The rules were that the derivative with respect to x of the natural log of x was just equal to 1 over x, and the derivative with respect to x of the natural log of u was u prime over u. And so this is what we'll be working with. Just when we take this derivative, we won't take a derivative, we'll take a partial derivative with respect to the appropriate variable. So I'll go ahead and get that out of my way, and then I remember what I'm doing. I'll make a little note up here to myself. The natural log of u is at u prime over u. And I'll go ahead and start taking derivative. The first order partial with respect to x. Okay, because I'm lazy, I'm going to do the easy thing first. And now I'll do the numerator. Let's see, the partial derivative, first term, well, there's no y, so it's just works out that it treats it just like a regular derivative. And so we get 16x cubed. Now the second one, I got the 2x squared, that's going to be 4x, and then the y squared drags along, so minus 4x y squared. And now I'll stare at it for a second and say, is there any way to simplify it? Well, it looks like all of the coefficients, I could factor a 2 out, and it looks like all the variables I could factor an x out. So I'll go ahead and do that. So that's going to give me 2x times 8x squared minus 2y squared over 2x times 2x cubed minus xy squared. And then these guys will cancel. And I get 8x squared minus 2y squared over 2x cubed minus xy squared. And there's nothing more I'll do with that, so I'll make sure it's properly labeled. And the reason I keep highlighting this business about making sure that it's properly labeled is there are two partial derivatives here. So I have to make sure that when I see this one on my page, I know that it's linked in some way to the fact that it is the partial with respect to x and not the partial with respect to y. Okay. Speaking of the partial with respect to y, let's go ahead and take that one. All right, h sub y, the first partial with respect to y. Going to be a fraction, denominator. Again, I'm doing lazy, so I'm going to do the easy thing first. My numerator needs to be the partial derivative of that argument with respect to y. So I'm going to take the derivative of this with respect to y. First term has no y's in it. Derivative of 4x to the fourth with respect to y is 0, so it just goes away. The second term, the 2 and the x squared are constant, so I'm only taking the derivative of y squared. Y squared is 2y. So that will give me, what is that going to give me? Negative 4 x squared y. Yeah, negative 4x squared y. Now I'll stare at it for a second and say, can I factor? Well, it looks like I could take a 2 out again. And it looks like I could get an x squared out. So I'll go ahead and do that. So that's just positive 2x squared times negative 2y over a positive 2x squared times 2x squared minus y squared. Right? Those guys will cancel. So that's going to give me negative 2y over 2x squared minus y squared. And that's my 8 sub y, my partial. Well, that's not too bad at all. Okay, moving right along. Uh-oh, this one looks like it's going to get ugly because I've got a quotient. So that means I'm going to need the quotient rule. And so let's see, I got the derivative with respect to x of u divided by v was v times u prime minus u times v prime over v squared. The derivative of a fraction is the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator over the denominator squared. Just now when we do these, we aren't taking derivatives. We're going to have to take partial derivatives. Okay. So the refresher's out of the way. Let's go ahead. Oh, a y squared got erased over there when I did that. Let's go ahead and start taking the derivatives. We'll start by taking the first partial with respect to x. Okay, it is the denominator, e to the xy plus 2 times the partial derivative of the numerator with respect to x minus the numerator times the partial derivative of the denominator with respect to, with respect to x. Let's see, that's going to be, well, the 2 doesn't matter because it's a constant, it goes away. The derivative of e to the xy is going to be e to the xy times the derivative of that exponent with respect to x, which will be y, over the original denominator squared. And so now I'll do this distribution and I'll clean up that multiplication and see what happens. And so I've got, let's see, 6xy e to the xy plus 12xy minus 3x squared y squared e to the xy over e to the xy plus 2 squared. There you go. Now I know at least one person out there is watching this going, well, looks like you could do some factoring there. And I'm going to say yes, but no. Yes, you could do some factoring, but no, you should not do some factoring. The purpose of factoring, the reason that we factored over here was because it canceled. nothing is going to cancel here. So why factor? Yes, we could. We could factor that. I could factor, what is that? I could factor a 3xy out of every single term in that numerator. But it's not going to simplify it in any useful way, so I'm just going to leave it alone. Same thing with that denominator. Could I multiply that thing out? I could. All it's going to do is increase the chance that I make a mistake and get this problem wrong. All right, partial with respect to y. Bottom multiplied by the partial derivative of the numerator with respect to y minus numerator times the partial derivative of the denominator with respect to y over the denominator squared. Cleaning up the numerator, let's see, I've got 3x squared e to the xy plus 6x squared minus 3x cubed y e to the xy divided by e to the xy plus 2 squared. And I'm going to use the same logic I used before, that while I could do some factoring in that numerator, nothing useful is going to factor out, so I'm not going to touch it. Okay. All right, moving right along. Some more examples. Okay. Let's see, manufacturing costs. Suppose that the manufacturing cost of a laptop is approximated by m of xy is equal to that, where x is the cost of processors and y is the cost of labor. Find the following. So what does this say to do? Well, it looks like I'm taking a partial derivative because there's an m sub y, but not only am I taking the partial derivative, but I am also then going to evaluate that partial derivative at the point 4,2, or for the input value 4,2. When x is equal to 4 and y is equal to 2, or when the cost of the processors is 4 and the cost of the labor is 2, however you want to word that. So what are the steps here? It looks like this is going to be take a derivative, a partial derivative, and then evaluate. Okay. So first step, partial derivative. M sub y of xy. First term, no y's in it, 0. Second term, only y's in it, plain old derivative rules. Third term, both variables are there, so now I got to use the partial derivative rule that says the negative 20x is a coefficient, a constant, if you will, times y, so the derivative of negative 20x times y is just going to be the negative 20x. 50 is a constant, so it just goes away. And there we go, there's my first partial derivative, but I'm not done yet because now I have to evaluate it at 4,2. So m sub y of 4,2 now means 80 times 2 minus 20 times 4, 160 minus 80, 80. Now I have no idea what that means, but I did it. I know that the partial derivative with respect to y evaluated at the point 4,2 is 80, positive 80, but I'm not sure what it really means yet. We'll get to that later in the section. All right, how is part A different from part B? Well, the correct answer is they're really not different. It's just take a partial derivative and plug in a value. All right. So I need to take a partial with respect to x to begin with. So the partial with respect to x will be 90x minus 20y. Okay. First term, 90x. Second term, no x, just goes away. Third term, partial derivative rules, I get negative 20y. So then m sub x of 3/6 will be, what is that going to be? That's going to be 90 times 3 minus 20 times 6. 90 times 3 is 270. 20 times 6 is 120. So what is that, 150? So m sub x, the first partial with respect to x of m, at the point evaluated at the point 3,6 is 150. Right. What about these two guys? Well, they're changing up the notation on us, but as long as I remember what that notation means, then I can just say, well, that just means the same as this. So that's just do what I just did, but now evaluated at 2, 5. So the partial m with respect to x of 2, 5 is just going to be that function, that derivative up there, that partial derivative evaluated at 2, 5. So 90 times 2 minus 20 times 5. $1.80 minus 100, 80. So the partial m with respect to x of 2, 5 is 80. Using that exact same logic, doesn't that just mean evaluate the y one? So grab this, evaluate it at 6, 7. So 80 times 7 minus 20 times 6. So 560 minus $1.20. What is that going to be? 440. So the partial m with respect to y of 6, 7 is 440. Whatever 440 means. All right, that's about 16.5 minutes, so let's call it good there. We'll come back and take a look at a couple more examples. Calorie expenditure for some animals. I'll see you all back here for part 3.